Ever wondered how AI computes probabilities efficiently? To answer that, we first need to understand what probabilities are in the context of AI. Artificial intelligence leverages probabilities as a tool to make predictions or decisions based on data. These probabilistic computations, while pivotal, can be complex and computationally expensive. Picture an AI trying to predict tomorrow's weather based on countless variables, a daunting task indeed. So how can we make this process more efficient? Enter the technique of variable elimination. So what exactly is variable elimination? In simple terms, it's a technique that helps us simplify the computation of probabilities. Now, let's delve a bit deeper. Variable elimination is a process that operates within the realm of probabilistic graphical models, specifically Bayesian networks. These networks are like a map of probabilistic relationships among a set of variables, structured into a directed acyclic graph. Variable elimination works by gradually removing variables from the joint probability distribution. Picture this as a complex equation with many variables. This process of elimination is done by what we call summing out or marginalizing the eliminated variables. It's like simplifying an equation, removing one variable at a time until we're left with only the variables we're interested in. But here's the catch. The efficiency of variable elimination hangs on the order in which we choose to eliminate variables. This order can significantly impact the computational complexity of the algorithm. A well-chosen order minimizes the size of the intermediate factors produced during the process, making it more efficient. This technique, variable elimination, is an exact inference algorithm. This means it calculates the exact marginal probabilities of variables in the Bayesian network. However, on the flip side, its computational complexity can skyrocket in the worst-case scenarios, making it less practical for larger networks. In such instances, we might need to resort to approximate inference methods instead. This might sound a bit abstract now, but stay with me as we're about to dive into how this works in more detail. With variable elimination, not just the process, but the order of elimination matters too. This might seem trivial initially, but it plays a pivotal role in determining the efficiency of the computation. Here's why. The order in which variables are eliminated can significantly impact the computational complexity of the algorithm. Think of it like this. You're doing a cleanup. If you randomly start throwing things away, you might end up with a bigger mess. But if you plan and organize what to get rid of first, the task becomes much more manageable. Similarly, a good elimination order in variable elimination is one that minimizes the size of the intermediate factors created during the process. It's like tidying up the computation, making it more efficient. So it's not just about getting rid of variables. It's about strategizing the order of elimination to simplify the computation. So variable elimination is not just about eliminating variables, it's also about doing it in the right order. But what happens when we have large networks? Is variable elimination still efficient? Well, as we delve into more complex Bayesian networks with numerous variables, we may start to see some limitations of the variable elimination technique. While it is an exact inference algorithm, providing precise marginal probabilities, the computational complexity of variable elimination can rise exponentially in the worst-case scenarios. It's much like trying to solve a maze that becomes more intricate as it grows larger. It's not necessarily impossible, but it can be exponentially more challenging. This can make variable elimination impractical for processing large networks. The sheer volume of variables and the computational resources required to handle them can be overwhelming. But don't fret, there are other techniques we can turn to. In such scenarios, we may need to resort to approximate inference techniques like loopy belief propagation or sampling methods. These methods may not provide exact results, but they can offer a more manageable approach when dealing with large networks. So, that's the gist of how AI computes probabilities efficiently using variable elimination. This powerful technique is rooted in the principles of conditional independence, simplifying the computation of marginal probabilities through the step-by-step removal of variables from the joint probability distribution. The magic lies in the elimination order, carefully selected to minimize the size of intermediate factors and, in turn, the computational complexity. However, Like all great things, variable elimination has its limitations. Its computational complexity can skyrocket, making it less suitable for large networks. Here, we may have to switch gears and employ approximate inference techniques such as loopy belief propagation or sampling methods. Remember, understanding these concepts is key to grasping the fascinating world of AI and its efficient computation of probabilities. Thank you for joining me on this journey, and I hope you found it insightful.